D2 is next. Newton's 3 laws. Now, the first law is a law of Galileo. Galileo observed that an object with linear velocity, traveling in a straight line, continues in the same direction unless a force acts on it. So before that time, they thought that you had to have some force to keep something moving. And that kind of, you can see why they made that conclusion, because everything on Earth seems to come to a stop, eventually. And that's because of frictional forces. But if you go into outer space and just have a mass that's moving, it's not going to change its motion unless you add a force to it. So unless you get near a planet or something, or you grab it or something, it's going to keep going in the same direction. So the incorrect way of thinking that you need to have a force to keep something moving, called the impetus, or the theory of impetus, dates back to Aristotle, 350 before the Common Era. So you're talking here like roughly 2,000 years, where it took for Galileo to come along around 1600 and fix that problem. So that's Newton's first law, the Galileo law. So we'll go ahead and list this as one, and that is that a body persists, I'm going to say it like this, in its state of rest or uniform motion in a straight line unless a net force acts on it. And it has to be a net force, because like with the bridge, there's many forces that are canceling each other out at each point, and we have a situation of statics where you're at rest. So for this condition to matter, you have to have all the forces be zero. So if all the forces are zero, you can either be at rest or in uniform motion. 2, when a force, and by force we mean a net force, when you add up all the forces, when a net force acts on a body, there is a change of motion, and we call that acceleration. There is acceleration, and that's going to be proportional to the force. And this equation that I'm going to write down, the famous equation, first I'll write the proportionality, the force proportional to the acceleration, but the equation is F equals ma. In other words, the force equals the mass times the acceleration. And that's going to give us a precise definition of force in terms of units also, because we'll have the kilogram here and meters per second squared. So that's going to define a force, and we're going to name that in the metric system after Newton, the quantity, physical quantity of the force. The third one is when a body A exerts a force on body B, body B exerts an equal and opposite, and we'll say oppositely directed force on A and the forces lie along a line joining the bodies. Now, I would like to have nicknames for all of these laws. So the first law here, nickname Law of Inertia. In other words, the mass wants to stay at rest or keep moving because it has inertia, we say, or the mass itself, the stuff, requires some kind of a force to make it change its motion or its status. The law of inertia. The second one you could call the law of force, mass, and acceleration, but I think it's cool just to say F equals ma. That's the law. F equals ma. Or you could say the law of force, mass, and acceleration, but I like to say F equals ma. Then this last one here would be the law of action and reaction. Newton's third law. Many years ago, I remember reading a high school physics book, and they described this third law by saying, you cannot touch without being touched. In other words, when you touch, see, I'm going to push here, but then this body's pushing back. Isn't that cool? So let's do it with the thumbs. Here's thumb A, here's thumb B. If I push on B like this, B is pushing back on me. Equal and opposite, and along the line, joining the two. Isn't that cool? I'd like to make a couple of comments about F equals ma. And the first thing is that since acceleration is a vector, we can put a vector sign over it, and that means force has to be a vector. Mass is a scalar. That's going to just have magnitude, but the acceleration has magnitude and direction. So that's the first observation. The second one, that even though F equals ma, either written like that or written in this form, is the common way to refer to Newton's law, it's technically not complete. Let's look at this. F equals m, and for the acceleration, I'm going to make it the derivative of the velocity with respect to time. That's what acceleration is, as we talked about earlier in other chapters. Okay, now, the question is, should that mass be outside here or moved inside the derivative? Well, it should be moved inside the derivative, and I want to explain why. So d dt, we have the mass in there now with the velocity. All right, that's the more general rule, say, than this one here, where the m was a constant, you pulled it out. Now, most of the time it's going to be a constant, but it's not a constant in a rocket problem. For example, if you have a rocket here, shooting out mass like this, then the mass is decreasing. Now, when a rocket leaves Earth, shooting stuff out the back, it's fighting gravity. Now, here's a rocket in outer space, traveling, and here's a rocket on the Earth that's trying to escape the Earth's gravitational field. So let's go ahead and work this out, and just assume that here you have simple case, one dimension analysis, the rocket's not going to turn around and do other stuff. So I go ahead and write this as without the vector sign, like this. Then I would have, for the force, I would have, say, the derivative of the first function in here. And when you have derivatives in a product, you do the first, say, the first one, the first derivative first, and that's times the second function, the v, and then plus the first function and the derivative of the second. So that's what we have. Now, in the case of a rocket, now basically you're looking at the mass. This is the mass, but if you're throwing mass away, then your mass is going to decrease. So in other words, dm dt is going to be less than 0. So let's say this is equal to some minus alpha by definition, where the alpha is greater than 0. So by putting a minus sign in front of it, then I get something that's less than 0. So if I do that, I get f is minus alpha v plus m dv dt. Now I'm going to add the alpha v to both sides of the equation, and I get f plus alpha v is m dv dt. Now what this is telling us is that if we're applying a force to the rocket, now let's say fictitious situation, say you're actually pulling on the rocket with some force F, like this. Let's say you're like have a rope, or let's say Superwoman or Superman, one of these superheroes is pulling a rocket like this. That would be this term. But then if you're shooting mass out the back by action, reaction, you're getting another kick to help the force. So see, this is important consideration. Newton's third law is being applied, and it makes sense that this is the way to set things up, and that the mass should be inside that derivative. Now, when you're trying to escape the Earth, the bad news is that this F here is actually working against you. It's going to be negative, and then you have to overcome that to get off the planet. Now, if you're in outer space like this, then there is no gravity around. You're, say, far away, so there's no gravity around. Then you're going to have this F is 0, but then that's going to be how you're propelling yourself and how the rocket's going. So we're not going to be doing rocket problems in this class. We're going to be looking at mass being a constant, looking at bodies that have constant mass. But I wanted to point out that this is the general form, and later in our course that we will do this, we'll define momentum as mass times the velocity, and therefore Newton's second law can be written as the force equals the change in momentum with respect to time.